Okay, so good morning, everyone. We are going to start a new topic today, but
Good
before that,
morning.
can you see the
Good
screen?
morning. Can
Can. Okay, so is this notes that same as the one that you have? Because my lecture version is a bit different compared to the student version. So is it same as yours?
Yes, madam.
Okay, cool. Then we are going to stick to this one. Okay, today we're going to start a new chapter called Momentum and Impulse. Okay, so, just like the title said, okay, we're going to look at two different things, which is a momentum and also impulse, as well as the relationship between these two items. So first, we are going to define momentum. So what is a momentum? So momentum is defined as the product of its mass and also the velocity. So we have P, but P is a vector, okay, which is equals to mv, okay, because it's multiplications between one vector and one scalar quantity. Therefore, P is a vector quantity. So make sure to put an arrow above it. Well, of course, in an exam, when it comes to calculations, you don't have to write the arrow above it, okay, but the definitions you need to include because it is a vector quantity. So all object has mass. So if an object is moving, then it has a momentum. So it has a mass in motion. That is a meaning. Okay, so that is the meanings of a momentum. And then the unit, SI unit for momentum is kgms negative 1. So how do I obtain kgms negative 1? Well, because the P equals to mv. M is in terms of kg, V is ms negative 1. So when you combine them together, the unit is kg ms negative 1.
Madam,
Yes?
yang arrow kat atas dalam kotak tu
Mm-hmm.
ada P dengan V je ke?
P dengan V sahaja because M is a scalar quantity. So scalar quantity, no arrow.
Okay.
So momentum is a vector quantity. So which means if the question asks you to calculate momentum, you need to calculate both. Okay, the direction and also the magnitude. Two things because of the terms vector quantity. So this is very important. So how do we determine the directions of a momentum then? The directions of momentum is same as the directions of velocity. So you look at the directions of velocity, which is the directions of motion, then that is the direction of momentum. So since momentum is a vector quantity, it has direction and we can resolve it into x and y component, like what we have been doing in the chapter 1 and chapter 2. So if you have a vector that is not moving along the horizontal component or vertical component, then you need to resolve it into x and y component. So in this diagram given, okay, the assumed angle is here. So angle is beside x component. So this is your y component. This is your x component. So the x component Px is equals to P cos theta. So P is your resultant value. Okay, P is your resultant value. So resultant value is the arrow in between x and y. Okay, the one with an angles. And then Py is P sine theta. Now, of course, if you have angles beside a y-axis, okay, like what we have been doing in a previous class. So this is your y, this is your x, this is P. If angle is beside y-axis, then you have to use P, okay, Py equals to P cos theta for y-axis, if angle is beside y-axis. Whereas for x-axis, okay, the Px would be equals to P, okay, P sine theta. So it depends on the locations of angle, right? If angle is beside x-axis, then x-axis we use cos. If angle is beside y-axis, then y-axis we use cos. All right, so that is momentum. Now, since momentum, it tells you it is related to the mass in motion, okay, then which means the values of momentum will be affected by the mass and also the velocity. So for instance, if you have a large object, for example, if you have a car, okay, car is very heavy. So if you have a car that is moving with a, let's say this car is 2000 kg, right, and it is moving at a 10 meter per second, this would be hard to stop because of mass. Okay, because the mass is large, it has a great mass, therefore it has a very large momentum. And another case, now what if you have an object with a very small mass, for example, bullet? Okay, so if you have a bullet, okay, and bullet often moving with a very high speed. So for example, this bullet, let's say, is 20 gram, okay, and it's moving at 400 meter per second. This is also something that is very hard to stop. So if something moving with a very high velocity, or it is moving, it has a great mass, then it will be hard to stop because it has a great momentum. All right. So P equals to mv. So it is being affected by m. P is directly proportional to m, and it is directly proportional to v. Therefore, if something has a very great mass or moving at a very high velocity, then it has a very great momentum. So if momentum is large, then it will be hard to stop. Okay, so that is momentum. Next, we're going to look at impulse. So impulse is defined as the product of average force and the time interval delta t during the force act. So which means now we have J and it is equals to F delta T. Now F is a vector, therefore J is also a vector. Okay, multiplications of a vector and a scalar quantity always give you a vector quantity. SI unit for impulse is NS, Newton second, or kgms negative 1. So it has two SI unit. All right, it has two SI unit. So the first one is a special SI unit because it comes with N Newton, and then the second one is in terms of base SI unit. Right. So impulse is also a vector quantity. And what is the directions of impulse then? Just now we have P equals to mv. All right. And then the vector P depends on the directions of vector V. Now you have J equals to ft. Therefore, we can say J depends on directions of the vector F. Okay, so directions of impulse is the same as the directions of the average force. So you look at the directions of force, then that would be the directions of impulse. So again,
Madam,
since, yes?
time interval tu tempoh masa lah.
Ya, tempoh masa. So kamu akan ada initial dengan final.
Okay.
So since impulse is a vector quantity, it has direction, and again, it can be resolved into x and y component. So again, the diagram given in your book is incomplete. The angle is beside x component. All right, the angle is missing. Therefore, for x component, your jx is equals to j cos theta, jy is equals to j sine theta. Okay, so that is impulse. So impulse, it depends on the force and also it depends on the time interval. All right, so next we have, okay, now this sentence I think is a bit weird. Okay, E is a bit weird. So I would say when two objects is in collision, the impulsive force against time is given by the area under the graph. The impulsive force. This sentence is a bit weird. Okay, why? Because actually what it wants to tell you is J is equals to area under the graph. Okay, when the objects collide. So how am I going to change the sentence? When two objects is in collision, impulse is given by the area under F against T graph. Yeah, that would be better. Okay, when two objects is in collision, okay, impulse is given by the area under the graph of, okay, under the, okay, this one, you move it here. Okay, the impulsive force against time graph. Right, impulsive force against time graph. So basically it tells you J is equals to area under FT graph. Okay, that is what it wants to tell you. So this sentence E, actually, you can just ignore it lah if you want. So J equals to area under FT graph. And now the questions, the notes, they give you a few examples. Okay, notes, they give you a few examples. So you have a few shape, few different types, few different types of graph. So first one, F against T. And now the average force, the force is in a straight line. Okay, so it means you have a constant force acting on the object. The amount of force exerted on the object is the same. So J is equals to area of the rectangle, because now you have a rectangle here. So area under the graph, therefore for the first case, first diagram, first graph, J is just equals to F times T. For second graph, now you have a triangle graph. Okay, and this is a graph that we will see quite often. Why? Because when you throw something, the force will slowly increase, and then when it hits object, then it will decrease. So in this case, now you have a triangle graph. Therefore, J is equals to the area of the triangle. Okay, area of this triangle. So which is equals to half times base times height. So in this case, you have 1 over 2 F1 T1. And then next one, what happened is the force slowly increase slowly. Okay, and then it's constant, and then it decrease. And in this case, you have a trapezium. So therefore, impulse is equals to the area of trapezium. All right, so how do we calculate the area of trapezium? Now, if you have a trapezium, okay, when we compare with the equation, J equals to 1 over 2A plus C, which part of the graph represent A? So A, let's say, is the base. Okay, baseline represent A, and then this upper line represent B, and C is the height of trapezium. Okay, C is the height of trapezium. So J equals to 1 over 2A plus B times C. Therefore, J is equals to 1 over 2. Now, T2 minus T1 plus T3. Yes, okay, so T2 minus T1 give you B. Right, this one is actually your B. And then this one is your A, according to my diagram. Okay, so times F1. So F1 is the height of the trapezium. So which is your C. All right, so that is how you calculate trapezium. Now, in case in exam you forgot how to calculate the trapezium, okay, you forgot what is the equation, then what can you do? You can split into 3 parts. Part 1, part 2, part 3. Okay, then you use the total area, which is 2 area of triangles and 1 area of a rectangle. So J can also be calculated by using area 1 plus area 2 plus area 3. Okay, which is 2 triangles and 1 rectangle. All right, and then the next one is a graph, a curve graph. So curve graph, we just use the area under the curve. Okay, so in this case, what are you going to do? You are going to integrate the equation. Okay, if you are given an equation for F, then you integrate the equations for F. Right, so J equals to integrations of F and then dt. So that is a last graph. Okay, the graph with no fixed shape, no certain shape. Okay. So far, any questions regarding the definition? So far, we're still at the definition. All right, we're still at the definition. So if you have any questions, you may ask. Okay, kita masih dekat part definitions lagi. We haven't looked at the relationship between the momentum and impulse. Okay, between momentum and impulse. Okay, now one of the typical example that we can use to see the effect of impulse, okay, is when you drop an egg. Okay, so now let's say you drop an egg from a building. Okay, you drop an egg from a building. Why is it not moving? Okay. So now if you drop an egg, so this is your F against T, right? F against T. Now you drop something, if the time interval is very, very short, okay, let's say now you have a large force over the short time, then in this case, egg will break. Okay, so this is your egg and then it will break. Okay, nice, not nice. Okay, now you're going to get an egg. Okay, so the egg will break. Now, if you drop an egg, okay, with a smaller force and then over a long period of time, then what is going to happen? This egg won't break. Okay, you're still going to get an egg, so the egg won't break. All right. So even though both of them they have a same impulse, okay, but if you have a large force over a short time, then the egg will break. But if you have a small force over a large time, then it won't break. All right. So same impulse, it doesn't mean same amount of force or same amount of time. It just means the same product of force and time. So it could give you different results. All right. So even though both of them they have same impulse. So area 1, area 2. So area 1 equals to area 2, but it doesn't mean they will bring you the same effect. They will give you the same effect. It look at what happens to the force and also the time. So first one, it has a large force. Okay, large force over short time. Okay, short period of time. And then the second example, we have just a very small force. Okay, and then it takes a very long time. Okay, over a long period of time to land on its surface. So for example, now you wrap an egg with a bubble wrap. Then that is a case for second area. So even though you drop it from a certain height, for example, and both egg they landed on the ground with the same amount of impulse, but first one you didn't wrap it, second one you wrap it with a bubble wrap. Okay, then it will give you a different result. All right, it will give you a different result. So don't get confused. Yeah, impulse, it doesn't give you it doesn't tell you much useful information. All right, what we want to see is what is the relationship between the force and time. Okay, so same impulse doesn't mean that it's going to have the same effect on our object. So you look at the graph. Okay, the graph will tell you quite a lot of information. And next, so why do we want to know impulse then? Okay, the reasons why we want to look at impulse is because impulse is a way to measure a change in momentum. All right, because it is quite impossible to calculate the force and time independently. So when an average force acts on an object during a time interval, the impulsive force is equal to the change in momentum. Therefore, we need the impulse momentum theorem. All right, because it is quite hard to calculate force every time. So what are we going to do then in order to calculate impulse? So we calculate it by looking at the change in momentum. Okay, by looking at the change in momentum. So now I can say J is equals to delta P change in momentum, and then J just now we have F delta T, which is equals to mv minus mu. All right, so most of the time we can measure impulse directly because it's quite hard to know the values of the force. Okay, for example, you drop an egg from a 10-meter high building. Okay, you want to calculate the force. Sometimes it's quite hard to calculate, okay, because of various factors. Therefore, we use a impulse momentum theory. Okay, impulse momentum theorem, where you can measure impulse by looking at the change in momentum. Okay, so that is one thing. Wait, yeah, I need to see. Because my notes is slightly different than yours, I need to check something. All right. Okay, so mathematically, J is equals to delta P and F delta T is equals to mv minus mu. All right, so that is a impulse momentum theorem. The only reasons why we want to use it because we want to calculate the impulse. And take notes, this equation, it comes out very often in exam. All right, usually the question is not that nice, just ask you to calculate, for example, okay, calculate the momentums of something, where you can apply P equals to mv. Or the question asks you to calculate the impulse. Okay, and then they give you F, they give you T, then you calculate impulse. No. All right. The question seldom that nice to you. Questions, what they will always did, they will maybe give you the time and then give you the mass, give you the velocity, and then ask you to calculate force. All right. Or maybe they give you force and then they give you a mass, they ask you to calculate delta P, something like that. So most of the times you have to use these two equations. Okay, and in fact, I would prefer to write it as J equals to delta P equals to F delta T equals to MV minus MU. So what does it mean when I write it in this form? Okay, it means other than a J must be equals to delta P, F delta T must be equals to F, it must be equals to MV minus MU. I can also use equation J equals to MV minus MU. I can also use equations delta P equals to F delta T. Okay, so basically they mean the same thing. So these four things, it depends on which information is given. Sometimes questions might give you impulse and then ask you to calculate final velocity. So you have to know how to link them together, impulse and then momentum, right? So compared to the definitions of momentum and definitions of impulse momentum theorem is much more important in your calculation. Okay, so we are done with the intro part. Okay, intro just asks you to know the definitions for impulse and momentum and also the relationship between that two quantity. So the main course today is actually the conservations of linear momentum. Right, ini adalah main course kita, main menu kita pada hari ini. So what is a conservations of a linear momentum? So principle of conservations of linear momentum states that the total momentum in an isolated system is constant. All right, the word constant is very important. Now, what does it mean by isolated system? If the question asks you to define principle of conservations of linear momentum, you must mention the term isolated system. Okay, so isolated system means that it is in an ideal situation. Ideal situations means that we assume there's no frictional force acting on our object, there's no friction between object and the surface. We assume there's no air resistance. Okay, there's no external force that will affect the motions of the object. Okay, there's no external factor. Okay, there are cause in the loss in the force. Therefore, we say it is in an isolated system. So isolated system is very important. All right, in physics, every law, every theorems that we form, they are all based on ideal situation. Okay, we often assume there's no air resistance, there's no frictional force, there's no energy loss, nothing. Okay, in order to form theory in physics. Therefore, when it comes to definitions, you need to mention, all right, principle of conservations of linear momentum is that it is a total momentum of an isolated system is constant. So an isolated system is a system for which the next external force is equal to zero. That is what I told you just now. We assume there's no external force. Everything is ideal. All right, that's it. An isolated system is one on which there's no external force or for which external force are balanced and added to be zero. Okay, so from Newton's second law, we say total force is equals to dp over dt. Okay, the changes in the momentum over the time equals to zero. Now, this equation seems like a new equations to you, right? Actually, it's coming from impulse momentum theorem. So just now we have J equals to delta P equals to F delta T equals to MV minus MU. This part actually is coming from, okay, your second law actually is coming from here. Okay, that's why I told you it will be better to write all four of them in one line, right? So rearrange the equations. You got F equals to dP over dt. And according to the definitions of a principle of conservations of a momentum, it tells you the total force is now equals to zero. Okay, because we assume net force is equals to zero. So rearrange the equations again. You got dP equals to zero. Therefore, the change in momentum is equals to 0. All right, change in momentum is equals to 0. So what does it mean? How are we going to write the equation? So we can say total initial momentum P initial is equals to total momentum in the final after collision. Okay, before collision and after collision. So even though two objects they collide with each other, okay, but the total momentum in both objects, okay, they are always constant. So delta P is equals to 0. Therefore, you can rewrite it as total P initial equals to total P final. So for example, now example given in your notes, head-on collisions. Now this is a very important terms. Head-on collision. So what does it mean by head-on collision? It won't tells you what is the directions of ball A and ball B. All right. Quite often you will see the terms two objects, okay, they undergoes a head-on collision with each other. So when you have the term head-on collision, means that these two objects must be coming from opposite direction. Now, why is it important to know that they are coming from opposite direction? Because it will affect the sign convention for velocity. So in this case, A is a positive velocity, so you have positive U, but in calculation, you have to use negative UB because UB is going to the left. Therefore, it is important to know the directions of object, right? And head-on collision, it's important because now it tells you you have two objects coming from opposite direction. So one of them is coming with positive velocity, the other one is coming with negative velocity. All right. So head-on collision, this is a very important terms. Okay, the hidden information here is it tells you two objects coming from opposite direction, and it tells you one of them must be a negative value. So during collisions, okay, so A and B, they collide with each other, and then after collision, they might move together or they might move in the opposite directions or same direction. It depends on the questions. It depends on the mass and also the velocity of each object. So after collisions now, in your diagram, it gives you A going to the left, B going to the right. Now A going to the left actually is a negative VA now, and then B is positive VB. So it is very important to know whether it is positive or negative. All right, so by looking at the directions of motion, then you should know whether it's positive or negative. So we assume net external force on this system of two balls is 0. Okay, the only significant forces during the collision are the forces that each ball exerts on one another. So during collisions, they have a very large external force, and then after collisions, the net force becomes 0 again. So basically, what is the things that we calculate? We calculate momentum before collision and momentum after collision. All right, so during collisions, we don't calculate it. So we look at before and we look at after, right? So the momentum of each of the two ball changes as a result of the collision, right? And therefore, the sum of their momentum is found to be the same before and after collision. So we are going to write it as MA UA, so the direction, this is a vector, plus MB UB equals to MA VA plus MB VB. All right. So this is the general equation. So after in your calculations, you then decide whether the velocity is positive or negative. Okay. So the sum of their momentum is found to be the same before and after collision. So which is a zone, okay, that gives you a straight line just now. All right. So before and after collision. Because the external force before collisions and after collision is 0. Okay, there's no significant changes in the force. So the momentum of two balls give you this equation. So although momentum is conserved in all interaction, not all interactions are the same. Okay, so momentum always conserve, but we don't have the same types of collision. There are a few collisions that we need to know. First one is what we call explosion. First type of collision. So explosion, it happens when you shoot something. Maybe you shoot it from a gun. Okay, and this is a tennis ball machine. So it shoots a tennis ball. Now explosion is very important. Okay, the term explosion. Why? Because it tells you the initial velocity of both objects is equals to 0. Initially, they are not moving. As you can see here, before explosion, they are not moving. So U is equals to 0. Okay, U is equals to 0. So this is explosion. Right? And then after it shoots a ball, tennis ball, what happens is that the machine will go backwards. Okay, and then the tennis ball will go forward. That is the characteristic of an explosion. Initially, both of them, they are not moving. And then after it shoots the bullet or it shoots the tennis ball, then two of them is going to move in the opposite direction. So in this case, what can we say? Okay, initial is 0. Why 0? Because UA equals to UB equals to 0. Therefore, initial momentum is equals to 0. And then equals to final momentum. Now they are both of them, they are moving. So MA VA plus MB VB. Okay, and two of them, they are moving in the opposite direction. Therefore, you should know that, one of the final velocity, velocity is negative. Is a negative value. So how do I know which one is negative? Now you look at the diagram. Okay, let's say I'm going to call the machine as an A. So this is A, and then this is B. So my VA should be negative. Okay, it should be negative, and then my VB is a positive value. When you substitute the value into the equation, when you substitute the magnitude into the equation, then you need to take into considerations the direction. So for explosion, the first things that you must know is initial velocity, initial momentum is equals to 0. All right. So the terms explosion itself, it gives you this information. And then the two objects, they are heading towards opposite direction after explode. Right? After explode. Second types of collisions, when multiple objects collide and then stick together. The keyword stick together. Okay. And then forming a single object with a common velocity. So now you have this M1 and M2. So one of them is moving according to the diagram, and then my V2 is not moving, 0. After collide, they stick, and both of them, they are moving with the same velocity. Okay, so this one I'm going to call it V. So both of them, they are moving the same velocity. So what can you say about this diagram? Okay, so when they stick together, they have a special name called perfectly or completely inelastic collision. Okay, perfectly or completely inelastic collision. So this one, both objects must stick together after they collide with each other. So in this case, based on the diagram given, we have M1 V1 plus M2 V2 equals to M1 plus M2 times V. Okay, the final velocity. So make sure you modify the diagram a little bit. All right, so the first one, this M2 is moving with V2. So even though it's equals to 0, you need to write it down. Okay, even though it's equals to 0, you need to write it down. And then after collide, they stick together. And only if they stick together, then we say they are perfectly inelastic. Okay, the term perfectly or completely, it tells you two objects stick together. Right, two objects stick together. Okay. So next one, multiple object collides. Okay, now multiple objects can collide and bounce off with each other, remaining as a multiple object. Okay, so means that after they collide, they are not stick to each other. Okay, so we have M, A. Okay, I'm going to call this A, this B, this A, this B. So if they are not stick together, then basically it's same as the first equation just now. Okay, so should be U, initial velocity. So MAUA plus MBUB equals to MAVA plus MBVB.
Adam,
Yes?
yang ni kita panggil collision apa? Head on lah.
Yang ini bukan head on, yang ini cuma collision sahaja.
Collision
Okay.
saja.
Kalau head on collision, two objects must be coming from opposite direction. But this
Direction.
one, obviously, B is not moving, only A is moving. So it is just collision.
Okay.
Okay, so it is just collision. So, right. And then, now, it is a very good question just now, okay? What types of collision it is? Now, when it comes to this example number 3, students often has a misconception. Misconception apa? Okay, students, they tend to assume when object they are not stick together, then when object they are not stick together, then it means elastic collision. Actually, it is wrong. Okay, tak stick tak bermaksud dia adalah elastic collision. Okay, stick together, case number 2, is definitely inelastic. Okay, because objects stick together, so it is definitely inelastic. But when it comes to this collisions number 3, it could be elastic collision, it could be inelastic collision. Just that it is not perfectly inelastic. Okay, it is inelastic but not perfectly inelastic if they are not stick together. Nampak tak beza dia? Kalau stick, kita kata perfectly inelastic. Kalau tak stick, dia cuma panggil inelastic. Okay, so for case number 3, there are two possibilities. First one is elastic collision, and then the second one is inelastic collision. It could be both. So kamu jangan tengok dia tak stick and then kamu terus anggap dia inelastic. That is actually a misconception. Okay, salah faham. So even though both of them, they uses the same equation, okay, which is this equation, but then there is one difference in between these two types of collision, and that is how we check whether this collision belongs to elastic or inelastic. So when it comes to elastic collision, what can we say about elastic collision? First thing, momentum is conserved. Okay, momentum is conserved. So what does it mean by momentum is conserved? Well, it just means summations P initial equals to summations P final. The second thing that is conserved is the total energy. Total energy is conserved. Okay, conserved means constant in an isolated system. So total E initial equals to total E final. Now the last thing is a crucial part, which tells us whether it belongs to elastic or inelastic collision, which is kinetic energy. Kinetic energy in an elastic collision is conserved. Okay, so total KE initial is equals to total KE final. Now, when it comes to inelastic collision, what can we say about it? So when it comes to inelastic collision, screen ada kan? Okay. So when it comes to inelastic collision, well, first thing, momentum is also conserved. So you cannot check whether it is elastic or inelastic by using momentum. Right? So momentum is conserved. Total P initial equals to total P final. And then again, total energy is conserved. All right? Total energy is conserved. So summations E initial equals to summations E final. But now the kinetic energy is no longer conserved. Okay, so this is the things that we use to check whether an object undergoes elastic collision or inelastic collision. Okay, it is not conserved. So summations KE initial is not equals to summations KE final. All right. So what is the difference between energy and kinetic energy then? Total energy, it could be the sum of kinetic energy and also maybe heat energy, your energy loss. So all those things, when you add together, that become total energy. That's why we cannot use total energy to check whether it belongs to elastic or inelastic, because we know that energy cannot be created or destroyed. It can only be transformed from one form to another form. All right, so therefore, before collision, maybe two of them, they have 100% kinetic energy. After collision, maybe they have 90% kinetic energy plus 10% energy loss. But the total is still 100%. All right, so therefore, you can only check with kinetic energy. So if kinetic energy is not conserved, then it belongs to inelastic collision. If kinetic energy is conserved, then it belongs to elastic collision. So how do we calculate kinetic energy then? Well, you use total. Okay, you use a total initial plus total initial plus total final. So kinetic energy initial, you calculate separately. KE initial equals to 1 over 2 m1 u1 square plus 1 over 2 m2 u2 square. Okay, or you're used to B and A already, right? So we change it to A and B. So A and B. And then you calculate summations KE final. So 1 over 2 MA VA square plus 1 over 2 MB VB square. And then you make a conclusion. If they have same value, then it is elastic collision. If two of them, they have different value, then you can conclude that it is an inelastic collision. So this is how you justify whether it is elastic or inelastic collision. All right. So if the question asks you, how do you know? Okay, how do you know that the collisions of two objects is a elastic collision? Then you calculate the momentum. Okay, there are two things that you need to show to prove that it is elastic collision or inelastic collision. So the things that you need to calculate to prove is the momentum and also kinetic energy. Okay, so kalau soalan suruh kamu buktikan bahwa sesuatu collision adalah elastic collision, dan kamu kena tunjuk momentum dia conserve, kamu kena tunjuk juga melalui pengiraan kinetic energy dia conserve. Okay, if the question asks you to prove that it is inelastic, then kamu buktikan bahwa dia punya momentum conserve, tetapi dia punya kinetic energy tidak conserve. Right, so usually we use momentum and kinetic energy to justify, to prove, okay, and a collision belongs to elastic or inelastic. So this one you write it down, okay, because your notes, I think they forgot to include it in your notes, so you write it down. All right, I give you 5 minutes to write it down. You can write it in a tidy way, in a okay, kamu tulis dia dengan kemas sedikit. Right, so don't always thought that if they are not stick together, then they must be elastic. Not necessary. Okay, it could be inelastic. So how do we know they belongs to which one? You check the kinetic energy. Okay, so 5 minit bagi kamu catat semua ini dalam dengan kemas dalam buku anda. Okay, dalam nota anda. So kalau ada sebarang pertanyaan, anda boleh tanya. Alright, so there are 4 types of collision. Okay, kita dah tengok 4 jenis collision. Explosion, perfectly inelastic collision, and then elastic collision and inelastic collision. 4 jenis. Okay, penting ya sebab dia kerap keluar dalam soalan objektif dan juga soalan subjektif. So make sure you write it down. Jangan tak tulis. Okay. So far, any questions regarding these 4 types of collision before I move to 2D momentum? Dua dimensi punya momentum. No question. If no question, then that is good. Okay, that's very good. So make sure you know how to distinguish, especially when it comes to elastic and inelastic. Next, okay, last part in chapter 3. Okay, since momentum is a vector quantity, okay, the equality is true for each component. Now you're going to look at each component. Now, what happens if you have two objects, okay, two objects that collides, but they are not coming from same direction? So for example, now you have an object, let's say this is your object A, and then this is your object B. Okay, object A and object B. So what happened is that now two of them, they move and then they collide with each other. So they move here, and then they collide with each other. So after collision, your A move in this direction, let's say, and then your B move in this direction. For example, okay, move in this direction. So how are you going to calculate them? How are you going to calculate? So you need to resolve, okay, you need to resolve the velocity into X and Y component. So for A, now let's see, this is A, so this is my UA, okay, UA. So UA, you need to resolve it, okay, you need to resolve it into UAX and then UAY, right? And then after collision, this is your V, let's say, so you need to resolve it again into V, A, Y, this is Y component, and then X component, VAX. All right, so whereas for B, what happened is that now before collision, this is initial velocity. So you have a UB. Okay, so just now is a VA. So UB, if you resolve it, you got a UBX and then UBY. Okay, and then for a B, object B, after collision, you have a VB. So VB, you resolve it, you got VBY, and then VBX. Okay, VBX. So how are you going to write it in the equations then? Let's see. Okay, so initial, okay, for X component, initial is PI along X component, which means what are you going to see is actually the X component for each object only. You're not looking at what happens to the Y component. Okay, you're not looking at what happens to the Y component. So for instance, how am I going to write the equation? Okay, I'm going to write it as MA, and now I just want the X component. So UA, so instead of A, I put in a subscript X, okay, in which I'm just going to use the velocity along X component. Okay, I'm just going to use the velocity along x component. I'm going to ignore y component. So plus mb ubx. Okay, mb ubx equals to ma vax plus mb vbx, right? So you're not going to see what happens along y component. You just want to see what happens along x component. M, you don't have to resolve it because M is a scalar quantity. So when it comes to scalar quantity, the direction is not important. Okay, the direction is not important. So basically, if you look at this equation, okay, this part, it actually represents P initial for A. All right, so this is a P initial x component for object A. So Pi, this is a Pix for object A. This is a Pix for object B. All right, and then this is the final. So this 2 is a final, but just for the x component. All right, just for the x component. So we are not looking at the y component. So this is P F final along x component for object A, final along x component for object B. Okay, so just now we have a momentum. Let's look at, okay, let me take object A. So object A initially is moving in this direction. Okay, so in my diagram, I put UA to work this direction. So the momentum actually is also along this direction. Okay, so this is your PA initial. And then when you resolve it, okay, this would be your PA initial along X component, and then PA initial along Y component. Okay, so you can put a IYA or IAY, AIY. Okay, both are fine. And then find X component. Okay, X component, Y component. So you need to resolve it, which means, all right, which means you need to resolve it. You cannot just leave it as UAX, UBX, VAX, VBX. All right, so you need to expand the equation. So let's say now I'm going to take the angles all beside X component. Kalau saya anggap angle dia semua beside X component, then what can I do with this equation? These equations will become MA UA cos theta A. Aha. Plus MB UB cos theta B equals to MA VA cos theta A final, and then plus MB VB cos theta B final. Okay, so saya ada theta initial, saya ada theta final. So the angle before collisions and the angle after collision, you need to take into consideration. So this is for a Y component. So for X component, what am I going to do? So basically for X component. So for Y component, what am I going to do? Same as X component. So MA UA now is Y component plus MB UBY component equals to MA VAY component plus MB VBY component. Okay, and then after that, you just expand it into cos and sine theta form. All right, so this is for a two-dimensional motion, 2D momentum. All right, so this is for 2D momentum. So 2D momentum means that your object is not moving on the horizontal or a vertical axis. Okay, it is moving in between X and Y component. Okay, it is moving in between X and Y component. So make sure you know when to use a 1D motion, when to use a 2D motion. And you will have more practice in your tutorial class. All right, so today I just shows you what is the equations to be used, how to use all these equations. Okay, you will learn how to use it in your tutorial class. All right, so far, any question? Ada sebarang pertanyaan?
Tak ada.
Boleh faham kan?
Boleh.
Harap-harap kamu boleh faham. Okay, yang 2D punya dia rumit sedikit. So nanti kamu akan belajar lebih banyak bila kamu masuk tutorial class. Alright. So let me see. Is there anything else that I missed out? Sebab nota kamu beza sedikit. Kena tengok satu. Okay. All right, so one last thing that I want to show you is, okay, we are going to go back to impulse. It is something that is not in your lecture notes, okay? So impulse, we have two directions, actually, when you hit an object together. So let's look at the hammer, okay? So how to determine the directions of impulse? Okay, we say it follows the directions of force. So we know that force is acting in both directions when you hit something. Okay, this is not your notes ya. Ini bukan nota kamu, so kamu tengok saja. So if you want to snap the picture, you want to take a screenshot, go ahead. So now you have this hammer, all right? So when you use the hammer to hit the nail on the wall, what happened? Now you have impulse acting on hammer, and you also have impulse acting on nail. Right? Because according to Newton's third law, when you push something, something will push you back. The force is acting in both directions. All right, so as you can see in the diagram, the blue color works. It says the force of nail on the hammer. Okay, so the force coming from nail, the nail push it back. When you use hammer to push the nail. So the one on the nail is the force of hammer on the nail. So impulse is in two directions, and you have to read the questions carefully. Okay, you have to read the questions carefully. See, question is asking for which impulse. Sometimes question can ask for impulse on hammer. Sometimes questions can ask for impulse on a nail. So what is the difference between these two things? Okay, it is a direction. So we have, okay, we have what? We have a J. Okay, J hammer equals to negative, okay, or hammer is a negative, right? Hammer is going left. So negative J hammer equals to positive J nail, right? So yeah, this one is a bit hard to write. Kamu sendiri tulislah kalau kamu nak, okay? Because it's a bit hard to write with my device. So hammer and nail, okay, you can calculate by using same equation, just that you have to look at the question. See whether the question is asking for impulse on a hammer or is asking for the impulse on nail. Then you determine whether you want to use the one with a positive value or the one with a negative value. All right? So it's 10 a.m. now. That marks the end of today's class. So if no questions, then you may leave the class now. All right? So this is just an additional info, something that is not in your notes. So if you want to write it down, you write it down. If you don't want to write it down, you just make sure you understand it. All right? See what types of impulse that we can have and how do we determine the directions of impulse. All right? So that's all for today. You may leave the class.
Thank you, madam.
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 Thank you, madam.